Okay, so I'm going to do this problem from the Serway book having to do with Newton's laws and circular motion. So you've got these two objects, m1 and m2, with different masses, 4 kilograms and 3 kilograms, tied together with a string, and it's rotating in a vertical circle. So kind of important to notice a vertical circular path, and that the two strings are always collinear, so that means that we don't have to worry about any bending of the string as they rotate around in a circle. At the top of its motion, you know the speed of m2, so that's the vector v which is drawn in the diagram. And basically parts A and B are asking you for what the tensions are of the two strings at this moment. Okay, so the problem's asking for tension. That's a force. So you know you need to use Newton's laws. You know you need to draw a free body diagram and a coordinate system. So let's do that. Let's draw a little bit more detailed diagram. Okay, so I've just redrawn the masses m1 and m2 and the string connecting them. And then what we should do is draw the forces. Notice I've picked a coordinate system which is pointing downward here. It's usually good to pick a coordinate system which is in the direction of your acceleration. So these two masses are traveling around in a clockwise circle, and so the acceleration of both masses is downwards. And for that reason, I picked my coordinate system to be downwards. It's usually best to pick your coordinate system in that direction. Okay, so let's think about drawing the forces. Okay, so I've drawn the forces and two velocity vectors. Notice that the velocities of these two objects are not the same. Just like when you're running around a track, the person in the inside lane has an advantage because they have to travel a shorter distance than a person in the outside lane. This m1, the outer mass, if you think about going around the circle once, has to travel a longer distance than m2 in the same time. So m1 is going to be traveling faster than m2. Now thinking about the forces, I've got gravitational force. Remember, this is a vertical circle. So vertical circle, I put a gravitational force m1 on m1 and a gravitational force on m2. And then what else is touching m1 is the tension, or is the rope, right, connecting m1 and m2. So that's T1 pointing downward on m1. And then m2 is a little more complicated. I have two ropes touching m2. I've got string 2, so there's a T2 pointing downward. And then there's T1, which is touching m2, and that's pointing upward. These two forces here are a Newton's third law sort of action-reaction, or you can also think about it as the tension in the rope is the same anywhere in that ideal rope. Okay, so we've got our free body diagram. We've got a nice sketch of the situation. So all we have to do now is proceed with the usual method of writing down Newton's second law. Okay, so now I've just isolated just m1. I have to write down Newton's second law for each of the two masses. And so normally I would do this, right? Sum of the forces in the x direction is m1a1x. Sum of the forces in the y direction is m1a1y, right? But there's really nothing happening in the y direction, and the only thing we have to worry about is the x direction as I've drawn it here, right? Pointing vertical. And so we can just ignore this second part, and we're just going to have one equation. So we're going to have here the forces downward, T1 plus m1g equals m1a1x, right? Notice everything comes with a plus sign because my coordinate system is positive pointing downward. So those forces are positive, and the acceleration, I don't need to worry about any minus sign for the acceleration. Then what I'll do is I will, we know this is centripetal acceleration, so I'll take, instead of a1, I'm going to write v1 squared over r1. So I have to think about what does this mean. This is v squared over r, centripetal acceleration. R is the radius of the circle that m1 is traveling in, right? So that'll be m1 v1 squared over the radius of the circle is 2L as given in the problem, right? Okay, so that's the one equation we get out of this. We get T1 plus M1G is M1 V1 squared over 2L. And now we'll do the same thing for M2. Okay, so I just copied the equation which we got from the previous slide from doing our mass M1. And now we need to do the same thing for M2. So just a little bit more complicated. We have two tensions. One of them is pointing upwards, so we have to watch out for that. We're going to have here T2, that's positive, plus M2G minus T1 is equal to M2A2, right? I guess I should put X here, right, since we're doing the X direction. So basically same idea, just I have that upward pointing T1 now. And then I'll do the same thing, put in here centripetal acceleration M2 times V2 squared over R2, the radius of the circle that M2 is traveling in. Now that's a different circle. That radius is only L, not 2L, right? So out of this I will get T2 plus M2G minus T1 is equal to M2 V2 squared over L. Okay? So we have now those two equations here, right? So this is what we got from doing Newton's second law. We got one equation, two equations in the two boxes there. And what is the question asking? In parts A and B, we want to know the T1 and T2. So we've got two unknowns here, T1 and T2. And what do we know in the problem? We know M1, we know M2, and we know L, right? And we also know V, the velocity 2, V2. This is V2 here. So we know those unknowns. And if I look in these two equations here, I've got, I basically know everything except I've got also a V1 sitting here. So I've got two equations, I've got two unknowns, T1 and T2, but the problem is I still have to deal somehow with this V1, right? What is this? Once I can get that in, I'm missing some information. I've got three unknowns, really. I've got T2, T1, and V1. And so I need another equation. I need to relate V1 and V2 somehow in order to finish this problem. So we'll do that on the next slide. Okay, so I've just rewritten the two equations that we got from Newton's second law here, but we said that there's something missing here. So we have to think about how to relate the two velocities of these two masses. I already said that it seems clear that M1 has got to be traveling faster than M2 because it's in a larger radius and they're connected by a string which doesn't bend, right? So if you think about it, imagine they're moving at a constant speed, right? The velocity would be 2 pi r divided by the period. That's the time, velocity's distance over time. This is the distance for around once. And of course the period t is the time around once, right? So if they were moving at a constant speed, this would be the velocity, right? And they are gonna, if they're moving at a constant speed, the period's gonna be the same for both of them. So I've got to have T1 equals to T2. So I would have here 2 pi R1 over V1 is equal to 2 pi R2 over V2, right? And the 2 pi's will cancel out. And so I get here that there's a simple relationship between the velocities. I get V2 over V1 is R2 over R1. And in this case, R2 is L, and R1 is 2L, right? Which is 1/2. So it tells you that V2 is V1 over 2, or V1 is 2 times V2. So it makes sort of intuitive sense that mass 1 is twice as far from the center of the circle if it's traveling along the same line as M2, if they're kind of connected by those two strings which are not bent. It's got to go twice as fast, right? So that's the last piece of information that we needed in order to solve the problem. So we've got sort of 3 equations for 3 unknowns, T1, T2, and V1. Everything else I know, those 3 equations, I can now solve the system. It becomes a math problem. All right, so now let's just sort of carry through the math, and we will be able to solve for those things. So here are my 3 equations for my 3 unknowns, and now I'm going to start solving this math problem. What's the tension in string 1 at this instance? So I'm going to just take that equation 1 and solve for T1. So T1 is M1 V1 squared over 2L minus M1G. And let me sort of clean that up a little bit. T1 is M1 times V1 squared over 2L minus G. Okay. Now, I don't know V1, but I know it's just twice as large as V2, so I'll just plug it in. I'll put the numbers in at the very end. T1 is M1. V1 is going to be 2 times V2 squared over 2L minus G. So T1 is going to be M1. There's a 4 on the top and a 2 on the bottom, so I get 2 V2 squared over L minus G. Okay, there's my formula. I know all those things, so I can plug in the numbers into that equation. Let me continue algebraically, and then we'll plug in the numbers at the very end. For part B, I just need to do the same thing for number 2. We'll just go ahead and solve that for T2. So T2 is going to be T1 plus M2 V2 squared over L minus G, right? Okay, and then if you want to get fancy, you could even substitute this formula in here for T1. So I could put here M1 2V2 squared over L minus G plus M2 V2 squared over L minus G. And then I can even simplify this a little bit. So I've got a V2 squared over L 2M1 plus M2. So I grouped the terms that had V2 squared over L in them. And then I've got here minus M1G and a minus M2G. So there's T2. Okay, so there's my formula for T2. Okay. We know all of those numbers. We know M1 and M2 and V2 and G, of course, we know. So now on the next slide, I will just plug numbers into that equation and show you the final answer. Okay, so I've just rewritten those equations from the previous slide and plugged numbers into those. So all of the things in these formulas, M1, M2, V2, L, and G, are things we know or are given in the problem, so I just plugged in those numbers. Notice that I'm plugging them in with the units and checking that the units work out. So for example, this first term, the one I just underlined, has units of meters squared per second squared divided by meters. So that's meters per second squared. That's the same units as this term, which is good. Anytime I add or subtract things, they have to have the same units. The whole thing is multiplied by kilograms, so the whole thing has units of kilograms meters per second squared, which of course is a Newton. And that makes sense because I'm looking for a tension, so it should have units of newtons. So the units work out. You can check that the units work out for part B as well. So all in all, we get these answers. For part A, the tension in string 1 is 216.8 newtons, and the tension in string 2 is 283.4 newtons. As for part C, which string will break first if the combination is rotated faster and faster? So at this instant, you can see that T2 is bigger than T1, but it's not totally clear whether that's always the case or not. So you have to think about, is T2 always going to be bigger than T1? It depends. So take a look at this free body diagram and look back at Newton's second law for this free body diagram. Remember, this came with an equation that looked like this: T2 minus T1 plus m2g is m2 times a, and a was v2 squared over L, right? So let me write this again. T2 minus T1 is m2 times v2 squared over L minus g. So take a look at the right-hand side. This is a positive number because v2 squared is obviously positive and L is positive. And g is a positive number. Remember, g is plus 9.8 meters per second squared. So the right-hand side is positive if v2 squared over L is bigger than g. If v2 squared over L is equal to g, then T2 is equal to T1. And if v2 squared over L is less than g, then T2 is less than T1. So it depends which tension is bigger, T1 and T2, depending on how fast you rotate it. But you can see that the question asks, if the combination is rotated faster and faster. So if I rotate it faster and faster, this term, the first term, gets big as v goes up, right? So as I rotate it faster and faster, that first term is going to get bigger and bigger, and so it will eventually, already when it's rotating at 4 meters per second, T2 is bigger than T1, and as I increase it even faster and faster, that will just get worse. So T2 will be bigger than T1. T2 is larger than T1 as V gets large. And so if the strings are identical, if one of those strings is going to break, it's going to be the one that has more tension, and so string 2 will break first, right? Okay, so there's the answer to part C, that string 2 will break first. So I hope you found this application of Newton's second law and circular motion useful.